And thanks very much to Barbara and Philippe for the invitation. I've really enjoyed my visit here and have enjoyed all the talks, at least up to this point so far. This is another one of those titles that's a placeholder that you give when you're not quite sure what you're going to do. It's fairly generic, and so, but in fact, it actually fits quite nicely, I think, with some of the other talks, and I'll try to make points of contact with some of those earlier speakers. So if we were to do a survey of the terrestrial planets in our own solar system and ask the question, what's the likelihood that these terrestrial planets have magnetic fields, then what's clear is that it's not a sure bet. Our nearest planetary neighbors, Mars and Venus, don't have magnetic fields at the present time. Mars appears to have had a magnetic field early in its history, and Venus we simply don't know. Mercury has a magnetic field, as we heard earlier today, which was a little bit of a surprise. But if you take these results at face value, then what we're talking about is sort of a 50% probability of a terrestrial planet having a magnetic field. If we were to look, though, to the gas giants and ice giants, then all of these planets have magnetic fields. Some are a little bit odd, but the point is that they are all able to generate magnetic fields. So there's something different about the structure or the way that these planets operate that make magnetic fields much more feasible than they are in terrestrial planets. We think that the basic processes that generate these fields are largely similar. They're convectively driven flows, relatively low inertia, strong influences of rotation that give rise to these sort of columnar structures of convection that Henri Claude showed, and that these styles of flow are very, very conducive for producing strong dipolar fields. And so if we think the mechanisms fundamentally in these planets, the processes that generate magnetic fields, are similar, then it must be something else. And certainly one of the factors that's got to be an important ingredient in this story is the fact that on terrestrial planets, they have these large silicate shells. And so the point of generating a dynamo and running the dynamo is that you have to cool the core. And to get the heat out of the core, you have to have it pass through this rocky silicate mantle, which is a bottleneck in the process of internal cooling. And it's this bottleneck, I think, that plays a huge role in deciding whether or not a planet is going to have a magnetic field. And so the kind of things that are going to happen are ultimately going to be driven by processes that happen in the mantle. So the overlying architecture, the overlying large-scale dynamics is also going to be set by the behavior of the mantle. And so this is just sort of a schematic of the kind of things that we think are happening in the Earth, and variations on these schemes of the type that Uli talked about may be happening in other planets. But ultimately you need the overlying mantle to be drawing heat from the core to allow these processes to take place. So the core cools, there's probably some small amount of thermal contraction that takes place. The cooling of the core also causes solidification of the core, and in the Earth this happens from the inside out, producing latent heat, excluding impurities that are not incorporated into the solid structure, as Dario was describing. And potentially, if we're cooling fast enough, we can also produce cold fluid at the top. And all of these sources of buoyancy are going to stir the fluid motions in the interior and ultimately produce magnetic fields. And the key point, I think, is that this process is ultimately controlled by mantle convection. And in some ways, I think, maybe to sort of just anticipate a little bit where I'm going, the fact that the existence of magnetic field is so sensitive on the efficiency or nature of mantle convection, I think will make magnetic fields a very useful proxy if we can measure them in other exoplanets and rocky bodies. Okay, so what we would really like to know is something about the heat flow that's coming out of the core, because the magnitude of this value will set the pace of all of these processes and set the amount of power that we've got available to drive the dynamo. And so we can come at this from a variety of ways. We can look and try to guess the thermal structure of the Earth today and make estimates of the heat flow that that thermal structure would produce coming out of the core. We have a variety of estimates of temperature near the surface, melting of oceanic crust, phase transitions, and other things give us estimates of temperature sort of in the range, potential estimates of potential temperatures on the order of 1600 Kelvin. And so we can extrapolate these along adiabats to the core mantle boundary and get temperatures sort of in this range. And we can do the same sort of exercise using constraints on temperature in the core. We have estimates of the melting temperature of iron, and particularly iron alloys, again, as Dario was suggesting, and we can extrapolate those values along an adiabat toward the core mantle boundary. We get values sort of in this range. And the point is that these values are different. We expect them to be different. And the origin of the difference, sort of in this range, is associated with the thermal boundary layer at the bottom of the mantle, which is what's ultimately drawing the heat out of the core and allowing these processes in the core to take place. So here's a zoom up of the processes that we expect. Here's the extrapolation of the temperatures to the base of the mantle, the extrapolation of the temperatures to the top of the core, this temperature difference. We can make various educated or maybe less educated guesses about some of these other parameters, things like the thickness of the boundary layer perhaps, or the value of the thermal conductivity of the minerals at the base of the mantle, and make estimates of this, the value of heat that that thermal boundary layer would be drawing out of the core. There's some question, and actually we don't know the answer to this, but whether or not there's an equivalent thermal boundary layer on the core side, we don't know. I'm actually going to argue that there isn't. But on the other hand, even if there was a thermal boundary layer on this side, it's probably on the order of a few Kelvin or so, and so there's no harm in interpreting most of this temperature difference to basically being the thermal boundary layer on the mantle side. Okay, so it's pretty uncertain. We get values sort of in the range of 5 to 15 terawatts, which are plausible. I think most people would argue that these are reasonable values. One of the things that's interesting about terrestrial dynamos in particular is the fact that the liquid iron has a very high thermal conductivity. And so as a consequence, if you have the core well mixed by convection, you would expect the temperature to be an adiabat. And as a consequence, you're going to have heat flux or conduction down that adiabat. And given the values of the thermal conductivity, you can get a substantial amount of heat that's just simply conducted through the fluid by virtue of it being well mixed. So these values, sort of in the range of 5 to 8 terawatts, are sort of approaching these values which we expect the mantle to be drawing from the core. So the point is, this conduction along the adiabat is actually in the ballpark of these values. And that's very unlike what happens in the mantle, for example. But with the recent revisions that Dario was describing, these values have gone up at least by a factor of 2. And so now we're looking at conducted heat flows sort of in the range of 10 to 16 terawatts. I think, Dario, your preferred value is around 15, if I remember right. So these values are very high. And now it's not only plausible that these are comparable to these values, but in fact, these values could even exceed these values. And there's all kinds of interesting things that happen when that occurs. So here's an image that Dario showed in his plot. It's just showing, or his talk, it's just a schematic of what we might expect to have happen if this heat flow at the top were to drop below the value that's conducted along the adiabat. So what we're looking at here basically is a plot of temperature as a function of radius. The inner core boundaries here anchored at the sensible melting temperature, we hope. And then if the entire core was well mixed, then we would expect the temperature to not deviate very much from an adiabat, which is sort of clearly here's the adiabat, and then we deviate off this toward the top. The problem with this particular state is that the amount of heat that I would conduct down that adiabat is greater than the heat that the mantle will take. And so there's a couple of possibilities. Either we could take the excess heat that's not being taken by the mantle and mix it back down, but it's more likely in the context of the core that the inertia of these flows is such that it's very unlikely that we would mix that warm fluid back down. And it's more likely that we would accumulate that heat at the top of the core. So what's going to happen is that the top of the core is going to warm up. The temperature profile will adjust such that the conducted heat flux matches the heat flux that the mantle is taking out. And this would be the state that we would expect. The point is that because this temperature deviates from the adiabat, it turns out that this region will be stably stratified. It won't participate in the convection. We can still have convection going on down here, driven by a combination of latent heat and chemical impurities driving the core here, but this part won't participate in the overlying dynamics. And so the interesting thing about this is, maybe to take another point, is that the thickness of this layer is going to depend a lot on how much this heat flux drops below the value, the hypothetical value that we could conduct along the adiabat. It also depends a little bit on the size of the inner core, because as the inner core grows, you're excluding these impurities. These impurities are only mixed into the region that's convecting. So this region is going to gradually accumulate light elements and become compositionally buoyant, and therefore encroach into this thermally stratified layer. And it's the balance really between the thermal buoyancy and the compositional buoyancy which sets the base of that layer. But what's interesting about this, if this was possible or if this existed, we might actually search for it in terms of the waves that stratification would produce or permit. And so it's possible actually that we could produce waves on the order of decade timescales, which we actually have some observations for. So we've known about these long period fluctuations in the magnetic fields and in the flows in the core for a long period of time. In fact, Dario showed a picture of the dipole field, and if you were paying really close attention, it was decreasing, but it was decreasing and fluctuating about a gradual decrease. And so what I've done here with that same data plot, the data set that he showed, is I've taken the linear trend, which is thought to be a long-term dynamic process, and this is what you get. You sort of see these fluctuations, which have roughly a 60-year period. There's some evidence for damping, but we've known about this for probably the last 40 years. And in fact, if you analyze various other attributes of the magnetic field, say things like looking at magnetic declination, a relatively recent study by Paul Roberts and company, you also pick out these sort of 60-year fluctuations. So we see these in the data, and the question is, could these be related in some ways to the presence of a stratified layer at the top? Okay, we also see decade fluctuations in the surface core flows. So these are recovered by looking at magnetic field variations at the surface and interpreting those field variations in terms of advection of the field around by flows. And so you can reconstruct the flows from the variations in the field. Now, we would expect on time scales of, say, several decades, for the flows to be strongly affected by rotation, and the motions that probably have the shortest time scales are probably associated with these geostrophic flows of the type that Henri Claude was describing. So these are flows that tend to be invariant in the direction of the rotation axis, and so if you have a flow, let's say at this particular point below the core mantle boundary, then the expectation is you would have a similar flow at the same point in the southern hemisphere. Of course, you could have a different flow on a different cylinder, but essentially the flows are organized onto these cylinders. And what we're actually observing and what this plot actually shows is a characterization of these azimuthal flows at the core mantle boundary. And so this is plotted actually as a function of the sine of the colatitude, so the angle from the North Pole. So what we're really thinking about here is the cylindrical distance from the rotation axis. So this cylinder here might correspond to a sine theta perhaps of about 0.2. Maybe this one is about 0.5 or something like that. And a small little cylinder that's right at the equator would correspond to that point. And so the thing is that when you look at these flows over the last century or a little bit more, they're both periodic in space and they're periodic in time. And so the question is this some sort of wave that we could then interpret and draw inferences from about the basic state of the core? One of the early suggestions, and it was originally proposed by Brzezinski, that these might be the torsional oscillations. The idea is that if these cylinders are threaded with a magnetic field, then when the cylinders move in opposite directions, that field component gets stretched. It acts like an elastic, almost an elastic restoring force, which will then set up these wave motions. But the point is that if you're going to explain variations in the flow with sort of these kinds of time scales, then the strength of the magnetic field that you require to explain these things is relatively low. And this has been known for a long time, sort of in this range of, say, 0.3 milliteslas. Some of the work that Henri Claude was referring to is the suggestion that these torsional oscillations have been detected with much shorter periods, much faster velocities, and the kinds of fields that are required to explain these are sort of on the order of, say, 2 to 3 milliteslas to get these waves propagating across the core, so going from here to here in periods of about 4 or 5 years. And so the point, I guess, is that if this is a correct interpretation of these torsional oscillations, then it leaves these waves unexplained. We still don't know then what these guys are. And it was that motivation, thinking about what these flows might be, to look at the question of whether or not a stable stratification at the core could actually explain and reproduce these features. Okay, so another contribution of Brzezinski was the Mach waves, which is I'm going to describe now. And he had so they involved the combination of magnetic fields, buoyancy forces, and Coriolis effects. And Brzezinski had the good sense to use the word Archimedes for buoyancy force so that we would get at least one vowel in the name of the waves. So conceptually, this is sort of how they work. Imagine this is a mode, and you could almost think of the football mode in seismology. Imagine that I've got a stratified layer here at the top, and it's relatively thin, just this region where the adiabat has departed, or where the temperature profile has departed from the adiabat. We have downwelling at the poles and upwelling at the equator, just a particular spatial pattern. So those flows, as they move down through a density stratification, is going to perturb the density field, and it's going to perturb the pressure fields. And so in a rapidly rotating flow, a pressure perturbation will produce a geostrophic flow in much the same way that you get geostrophic or cyclonic flow around a pressure low in the atmosphere. So the dominant component of these flows are going to be these geostrophic flows, which have much the same structure of the flows that we were looking at in those plots, sort of almost geostrophic. What's happening here is more or less what's happening there. But when these layers are threaded with a magnetic field, these zonal flows will introduce a certain amount of friction, and that friction will then produce either a poleward or an equatorward flow superimposed on top of these things. And so after half a cycle, these flows reverse and they can change sign. But the point is that for plausible values of some of these things, we can actually get waves which are in the order of several decades and potentially explain these observations. So let me just show you one example, just a numerical calculation of what some of these modes might look like. In some ways, it's not that different from calculating seismic modes, except you're incorporating fluid dynamics, magnetic fields, and buoyancy. So what I'm plotting here is a small section at the top of the core. One is the core mantle boundary, and this is roughly 4% below that. And this represents the radial velocity as a function of latitude, the azimuthal velocity, and this is the large component of the flow, and then the corresponding meridional flow, which is associated with this. And so for the parameters that I've chosen, I've picked ones with about a 58-year period because I'm going after that 60-year oscillation. And so again, you see upwelling here, downwelling here. There's a corresponding zonal flows that are associated with the pressure perturbations that these radial motions produced. Okay? And again, they have the structure that we require to explain the zonal flows that we see in the core. We see, you know, at mid-latitudes in the north, we see similar flows at mid-latitudes in the south. Similar at the poles, close to the poles, we see similar flows in the South Pole. And again, these flows we'll come back to in a little bit. The key parameters that go into this model, well, there's three, really. One is the strength of the magnetic field that threads through this layer, but using some of the results that Veronique described this morning, we think we actually know something about the strength of the magnetic field in this region. So that leaves really two parameters. One is the thickness of these layers, and then the other will be the strength of the stratification. And we'll assume that it's maximum at the top and decreases to zero at the bottom, which is consistent with what we'd expect with that simple model of thermal stratification. Okay, well, let's see how this works. So we can calculate modes. You give me the thickness, you give me the buoyancy frequency, I'll crank out a set of modes for you. And the idea was to actually see if we could take some small linear combination of these modes and reproduce the observed flows. So what I'm showing you here are the observed flows from Jackson, now just over a 60-year period, a much shorter period than the original flows that I showed. Again, it's that azimuthal component, sort of on this order of magnitude. And what I've done is I've picked a value of h and the maximum buoyancy frequency at the top of the core, produced a set of modes, and then tried to fit the lowest frequency 6 modes to those flows. And you get some measure of misfit. But then you start to iteratively adjust h and n max to see if you can get a better fit. And so this is the outcome of that fitting procedure. And in fact, these are really close. I have to be very careful when I put these on the screen to make sure that I actually label them correct, because there's really only some small various areas here where they're a little bit different. Now you could argue I'm taking a wave-like motion here, and I'm fitting modes to it, so almost you'd argue this must be certainly going to be successful, right? But in fact, it turns out that there's a relatively narrow range of these values of h and the buoyancy stratification that actually reproduce these flows. So it's really quite a narrow range of parameters that we can actually find this success. Most cases, we just get disaster. And I think the point you have to remember is that we're not only fitting periodic functions, but they have the right phase and the right amplitude over a period of time. Okay. So let's come back now to these zonal flows. So the idea here is that I've fit these waves to the zonal flows, and I can come back and ask the question, what are the consequences of those much weaker meridional flows that are associated with these waves? Okay, so again, what I've done is fit these to the observed flows. These are not observed currently in the magnetic field flow model, simply because the assumptions that are used to invert these flows don't permit those flows. But simple scaling arguments give us an estimate of how large those flows are expected to be. They depend on things like the thickness of the layer. They depend on the strength of the magnetic field, here represented in terms of the alpha velocity, using the same symbols that Henri Claude used. And you get something on the order of maybe a little bit less than 10%. So these flows are a lot weaker than the dominant part of the flows. But we can ask the question, what would be the influence of these flows on the magnetic field? For example, if we put these into a magnetic induction equation, the meridional flows here, that's going to take magnetic field and sweep it toward the poles. So it's going to actually cause the dipole field to get a little bit stronger. And conversely, the other half of these waves, when these flows reverse, it's going to sweep magnetic field away from the poles and actually lower the strength of the dipole a little bit. And so the point, I guess, is that if I've fit these flows to the core flows, then I can make predictions of what the dipole variations would be with no other assumptions and with no other adjustable parameters. We just stick it into this equation and ask the question, what happens? Okay. So here's the fits to the Jackson flows. Again, fitting these flows, putting it into the induction equation, and actually predicting what the dipole variation would be over that last 60 years. And so the blue line is the prediction, and the green dots are the GUFM model, which are the model that Andy Jackson used to construct his flows in the first place. And the agreement is staggering. And in some ways, again, I have to remind you that there are absolutely no adjustable parameters, that once I've fit the zonal flows to these waves, that's it. Everything else is sort of prescribed. So when I saw this, I was actually very impressed, I have to say. And I sent it off to Nature, and it turned out the reviewers weren't as impressed as I was about the flows. And they made the comment that, you know, these are very nice, but on the other hand, there are more modern flows that have been recovered using both historical observations as well as satellites, and I ought to be able to explain those as well. And so taking the same modes that were fit to the Jackson model, without any adjustments, just fitting them to these more modern flows, you get this result, which again is reasonable in terms of amplitude and phase and other things. And so this was enough to convince the reviewers, and they ended up deciding to publish the paper. But it's interesting, I think, that these results, to fit these results, you actually do require some of these higher conductivity values that Dario was talking about, which are the kind of values that would give rise to the thermal stratification in the first instance. And the reason for that is as follows. The amplitude of these dipole variations are going to be really dependent on the strength of this flow. And this flow is going to be really dependent on the thickness of the stratified layer. And so it turns out that if you try to fit the flows with a conventional value of electrical conductivity, maybe a value of half this, you're inclined to make much thicker stratified layers, because if you make the layers too thin, the damping is too much and you don't predict the zonal flows very well. But if you change the conductivity to a higher value, you fit the flows with a slightly thinner stratified layer, you get larger amplitude meridional flows, and you're able to reproduce these. So the ability to fit both the zonal flows and the dipole fluctuations does seem to suggest that there's you require higher electrical conductivity. Okay. So let's now come back to the original motivation for this whole thing. I was making the argument that if this heat flow was less than the value that you could conduct up the adiabat, that you will develop this stratified layer. It will have maximum sort of stratification at the top. That stratification will decrease and eventually vanish at the interface between the stratified layer and the convecting region. And quite a long time ago, a model that I worked on with John Lister, shortly after when I was a postdoc, made predictions about the thickness of this layer given heat flux from the core mantle boundary and given a size of the inner core. And so if you were to take the model with an adiabatic value of about 15 terawatts, which again I think is Dario's preferred value, and we adopt a heat flux of 13 terawatts, this is the value that's actually going into the base of the mantle, then you can get a layer thickness which is about 140 and a buoyancy frequency at the top which is about 1.5 times the rotation rate. So what I should point out is that I've chosen this heat flux so that I reproduce the thickness of the layer that we get from the waves. But what I thought was actually quite encouraging is that the buoyancy frequency that you predict with these layers is actually not so far away from what we recover from the waves. So at least there's a self-consistent story. Okay. So actually I'm going to conclude, and I'm hoping that there's going to be lots of questions and hopefully lots of questions. Well, I'll motivate you. So the energy for the dynamo depends on core cooling. So I think really the issue of planetary dynamos in terrestrial planets is really all about the mantles. I think the mantles probably play a dominant role in whether or not these things work. With Earth, with plate tectonics, relatively efficient way of cooling the interior, I think we can sustain the height flows that we require to maintain a magnetic field. But we have evidence on the basis of these waves that in fact, even in the Earth, the value might not be above the adiabatic value. Okay. So we have thermal and chemical buoyancy that are playing an important role today, but with these heat flows, sort of in the order of 13 terawatts, the inner core probably formed 500 million years ago, so around the time of the Cambrian. And so prior to that, these flows would have had to have been sustained by thermal buoyancy alone, which would require us to have more vigorous thermal convection. And so to me, at least, if we have evidence for a field going back this far, we would expect there to be plate tectonics at that time. We see evidence for Mach waves at the top of the core. They give us an estimate for the heat flux that's coming out of the core. But prior to this date, we're going to have this value up above the 15 terawatts in order to drive the dynamo. And then lastly, I think this wave motion offers a new tool or vehicle for investigating the core. We can think about the contribution from non-zonal modes, which will contribute to field variations and should be consistent with the same stratification structure that explains the zonal flows. We want to understand how the modes are excited. It's probably by virtue of buoyant fluid rising up and hitting the base of these layers. And so why are the flows in the core exciting the modes that we see? Why don't they excite others? I think it's going to tell us quite a lot about the style of convection in the core. And I think there's going to be also some coupling to deeper flows which will be required to explain the length of day variations. Thanks.